Hey, welcome back to Earth Sky Monday interview live thingamajig. And we are back for another session. And this time we are going to talk with Stacy McGaugh. Hi, Stacy. How are you?
Hello.
Now, Stacy is at Case Western Reserve University in Ohio, and he's an astronomer, a professor of astronomy there. And he studies dark galaxies, dark matter, theories of modified galaxies, which is going to be key to what we're talking about today. He is an expert on low surface brightness galaxies, which are objects where the stars are spread thinner than they would be here at home in the Milky Way. And he also demonstrated, which we're going to talk about too. We're going to talk about cold dark matter today. He demonstrated these dim galaxies appear to be dark matter dominated, and that these provide a unique set of tests for theories of galaxy formation and for modified gravity. Stacy, the first thing that we want to ask you is the Big Bang safe? You're not getting rid of the Big Bang on us, are you?
So no, the Big
No.
Bang is fine so far as I'm
Okay.
aware. Um, we will entertain some pretty deep and challenging ideas in this talk, but
We sure
I
will.
think it's very well established empirically that the universe is expanding. It went through an early hot phase that gave us the nucleosynthesis that provided the
Mhm.
hydrogen, helium, lithium we have in the universe, and also left behind a relic radiation field that we know is the cosmic microwave background. So
Right.
that framework, I think, is true, has to be true in any theory. It's getting the right theory that's going to be the issue.
Awesome. Okay, great. Well, I think that's a load off my mind. I was worried that the Big Bang might be in trouble, but no. But
Not for me.
not from you. Well, there is some evidence mounting a little bit here and there that the Big Bang might not be what we think it is, or maybe it is. We don't know. Is that right? Or
Well, it's always been a target, right? People there are people who don't like the idea,
yeah.
and so there is a lot of crazy talk from that side. So you have to be careful of that. On the other
Okay.
hand, one has to be careful not to dismiss legitimate things by association. And so, it's certainly possible that there might be some kind of evidence we should reconsider. Um, and I've spent a lot of time in my career trying to weigh how that is, what that is. So, in my opinion, the Big Bang, as we know it, is not in serious jeopardy. I would say
Okay.
that the specific theory most of us believe in nowadays, the so-called lambda cold dark matter theory,
Right.
that's more open to question.
Okay. So that brings us back to the paper that you and your team put together, and you're the lead author here. And I understand you looked at some data from the James Webb Space Telescope all the way back, as far as you can see, to the earliest structures in the universe. And we're talking about an era when the whole sort of general mishmash, oops, sorry about that. In other words, everything was brand spanking new. The cosmos was fresh faced and innocent, and it had no idea what was coming for it, did it? Oh, so I mean, but we're going to be talking about the most basic theory of how galaxies and early structures in the universe began, right? How far back are we talking about?
I would like to say all the way, but not quite all the way.
Not quite all the way.
So in the first billion years or so, and especially
Hmm.
the first half a billion years, now
Okay.
billion years, give or take, that's a long time to you and me. Um, for the universe, that's the first month on the calendar, right? The
Right.
universe is 13, maybe 14 billion years old. And so we built James Webb to look and see how galaxies formed at the very earliest times. And it has succeeded marvelously in doing that. And it is revealing to us things that happened at such ludicrously high redshifts that we are talking about the very first billion years, less than a month on that cosmic calendar. It's all happening in January, and a lot of it's happening in the second week or so.
Of the
And that,
cosmic calendar.
yeah, and that's kind of earlier than a lot of us expected.
Okay, so when we're talking about redshift, and that's in terms of a Z, they call it the
Yes,
Z. Right now is 0. Is that correct?
that's
Z
correct.
0, and so the Z that we're going to be talking about is about 2 or 3. Is that right? Where are we? What are we looking at?
Well, that is a great question. So, redshift quantifies how much the light has stretched since it was emitted, and the
Okay.
universe is expanding. So, the further back in time, the closer to the start of the Big Bang, the more stretching, and so the higher the redshift.
Okay.
And so, the relation between the look back time, was it a million years ago, a billion years ago? How long have those photons been traveling? Uh, it's more, the more the redshift is, but most of cosmic time is between now and redshift 1.
Right.
And that's a lot, right? That's a lot of
Mm-hmm.
time, 7
It
billion
sure is.
years, give or take. And it's corresponds to taking a spectrum and basically doubling all the wavelengths, right? So if you see some
Mhm.
spectral
It,
line,
it sort of does that.
yeah, exactly, and that shifts by 1. That means a whole 100%, basically, um,
Right.
and that redshift can go arbitrarily high, and you just get more and more shifted. And so,
The further
um,
back you go in time.
already redshifts 2 and 3 are pretty early in the universe.
Mm-hmm.
James Webb is showing us things at redshift 10 and above, even.
Wow.
And so, yes, wow. I remember some of the early claims in the 1990s when James Webb was basically, we decided we have to build this thing all the way back then.
Yeah.
And there were claims of things at redshift 7. And we're like, nah, no way, that can't be true. And I remember talking to theorist friends who were categorical, there is nothing above redshift 7. And you fast forward now, and that was a reasonable attitude.
It was back then.
Yeah,
It's not
exactly.
now, though. So,
But
so okay. So, what specifically you focused on? Your paper is called "Accelerated Structure Formation: The Early Emergence of Massive Galaxies and Clusters of Galaxies." And what is it? What did you see back there? You expected to see protogalactic. Well, you didn't expect to see protogalactic fragments, but if maybe do we need to talk about Lambda CMD here, or what did you
absolutely,
see? Why don't you just tell us what you saw and what are what are protogalactic fragments and did you find them? Let's start right there. How does that sound? I'm
so
sorry.
what are we talking about here?
Exactly. Yes.
So okay, so we live in galaxies today that are big at redshift 0, things like the Milky Way, and we
Right.
look out in the universe around us and we see other island universes like that, basically big collections of stars like our own Milky Way with lots and lots of empty space between them. And
Mm-hmm.
then that stretches out into larger scale structures, clusters, voids where there basically are no galaxies, walls and filaments between them, this whole tapestry of the large scale structure of the low redshift universe. And
Okay.
so we want to know how that came to be, and we have a lot of ideas for how that is. So that's where this lambda cold dark matter comes from. And the lambda part is what you also hear people talk about, dark energy. That's what makes the expansion rate of the universe accelerate.
Mm-hmm.
We don't care too much about that for our purposes
No.
today. It just sort of sets the framework in which all this happens,
Right.
what
Right.
that background expanding universe is, that is the hot Big Bang. The cold dark matter matters a lot. So the early
Yes.
universe was, we've got observational constraints that predate even what JWST shows us. So
Meaning
the
that there are things that show that CMD is happening. Is that what you
that you
say?
need something extra. Let me put it that
Right.
way. And
Okay.
our first
Exactly.
best guess for what that something extra was this cold dark matter. And one reason for that is that the microwave background, that cosmic relic radiation field from the hot Big Bang, That comes to us from a redshift of 1,000, even a little more than that, when the universe was only a few 100,000 years old. So that's sort of a baby picture of the universe. And it had no structure to speak of. So we see this rich amount of structure today. The early universe is observed to be extremely uniform. And the question arises, how do you get here from there?
Where did the structure come from? Was there cold dark matter that caused things to start clumping up, and then we built on a hierarchy of small to large? That's
Exactly.
Lambda CMD. But then there's another approach, isn't there?
Well,
That
well,
well,
so
let's talk about. I'm sorry. Please
I
continue.
think we should talk about the cold dark matter a little more, because what you said is
Okay.
exactly right.
Okay.
But it's
Good.
worth elaborating, I think, what we
Please.
expect
Please
from
do.
that theory. And in fact, most of the paper is about that. And it's important. A theory is only as good as its prior. What do you predict? Because you can always fudge it afterwards. So it's really important to establish what you expected going in. And the idea of cold dark matter was to take that very smooth early condition of the universe and give something extra to make the structure grow. So gravity is an attractive force, so it'll make
Mhm.
the little, we do see tiny density fluctuations in that early radiation field, but they're tiny. Um, and so gravity will take those things and make the rich get richer. So something that starts out with a little extra density will become more and more dense. And the idea is that eventually becomes a galaxy. The problem is that gravity, as taught to us by Newton and Einstein, is not strong enough to get here from there. You can't get here from
Ah,
there. And so you need something to goose the process. You
some kind
also
of
need
energy
something,
of activation.
yeah, so some extra something. And so the idea was that we would add in this cold dark matter. It was stuff that didn't interact with the photons by choice and construction. And then it could grow without leaving too much of a scar on the microwave background. And so we need that. We need something extra anyway to make the structure grow to get here from there. And so that was one of the reasons that we invented this stuff in the first place. Now that
It
brings us
has
to
something has to be there.
we need to get here from it, right? There are other
Right.
mysteries like baryogenesis. Why is there more normal matter than antimatter? We still don't really understand that. So
No,
there are fundamental puzzles still, which is kind of cool.
it
Um,
is, isn't it? Anyway,
so once we have the cold dark matter, we can calculate in linear perturbation theory, which is elegant. You just take the basic solution that Einstein gives us for how the universe expands and just tweak it a little and show how that structure should grow in the presence of the cold dark matter. And that's been a
okay,
very successful theory. It
right.
shows how you can get here with lots of structure from there way back when with very little structure.
So its predictions have held up for the most part, haven't they? Lambda CMD is a fairly strong theory in that regard.
Yes, yes, and no.
And
So,
no, okay.
I mean, Lambda CDM is an excellent fit to all the data at low redshift for large scale
Ah,
structure. Um, we didn't just get there. Our initial best guess was what we used to call standard cold dark matter without the
mhm.
lambda, and that failed badly. We knew we needed the cold dark matter, but that didn't actually work to explain large scale structure by itself. We had to do something different. Long story short, that became the lambda. So we migrated from the 80s, believing in standard cold dark matter, having all sorts of issues in the 90s, to by the end of that deciding no, it's lambda cold dark matter. And I mention that in part because it's easy to look at the successes, and there are plenty of Lambda CDM now, and think, oh, well, it's predictive. It wasn't that predictive. It was fitted because
Ah,
we started at something different. Now, having said that, it fits lots of different things that it wouldn't necessarily do. There are independent constraints. So that I find impressive. But we did not expect the amount of large scale structure that we see. We were surprised by that. We were gobsmacked as we made
So
surveys.
that now,
Galaxies.
so we're talking now about the data that you examined from Webb that led to the paper, and what you found were not fragments or building blocks, proto-galactic fragments. You didn't find those in the numbers that you expected to. Is that correct? Is that
That's correct. So basically,
okay?
what we had before the Webb observations was very smooth starting point, very lumpy finishing point. We wanted to know what goes on in between. So that's what Webb is telling us now. And what Lambda CDM predicted was that you had to boil up very slowly and gradually out of
Right.
this smooth initial condition. And that's what makes these protogalactic fragments. And it is the hierarchical merging of these things, little things merging to form bigger things, merging to still form bigger things that are supposed to form the galaxies that we see today. That
And
makes perfect sense mathematically, but it takes a long time
a
to
very long, drawn out process.
exactly. And
Okay.
so that's what we're not seeing. We
No.
expected at these very high redshifts that JWST is revealing that there would be lots and lots of small proto galaxies. And instead, what we're seeing is a surprising number of what looked like God just said, here's a galaxy. Here's a galaxy. There are big island universes already in place at very early times, bigger than they should have been in this standard theory.
And some of them were the star formation had essentially ceased. Is that correct? I mean, that's another indication of age, isn't it?
So yes. So again, stepping back in time, we've been studying galaxies for a long time, and without knowledge of that Lambda CDM theory that we were just talking about, people just looked at the properties of galaxies and inferred already that some of them were old. They stopped forming stars a long time ago, and it looked like they formed almost all of their stars very early on. The brightest elliptical galaxies fall into this kind of category. And then, you have, well, but from a theoretical perspective, they should have formed in these little things. And that for a while was known as a downsizing. Naively, from this picture, you would think that the biggest things that are these elliptical galaxies, they would have formed last. And so they should have the youngest stars, but they have the oldest stars. And so, yeah, exactly. But
wait, what?
yeah, exactly. And so this actually has a reasonable explanation in Lambda CDM, is that there's a difference between when the stars form and when they assemble into a galaxy.
Oh, so older galaxies or older stars form into new galaxies. Is that
exactly? So these little protogalactic fragments could be where all that star formation happened, and then they merge to assemble into the bigger giant galaxy. That was the picture going in.
So that was the theory, right?
That's the idea.
Yeah. Okay, but you didn't. That's not what you saw. That's not what Webb discovered.
That's not what Webb is seeing.
Okay.
And let me give credit to the entire astronomical community here. There are many astronomers working with Webb on these data. We've played a fairly small part in analyzing it, and it really is a community effort first to build this, really elaborate facility, launch it into space, and then contend with the data that we come back from it, which has been the proverbial fire hose. So yes, but what people recognized very early from the first images basically was that there were brighter galaxies at higher redshift than were expected in the scenario we just talked about.
Okay. All right. And so in the paper, you and the team make an argument that the imagery you're seeing, or not the imagery, it's not actual visible light, is it? It's what you're seeing is supported by an alternate theory of cosmological formation, which is modified Newtonian dynamics, right?
Correct. That's right. Yeah.
What the heck is that?
What the heck, indeed. I've been asking myself that question for going on 30 years here. And
Well, I hope you came up with some good answers you can share
Well,
with us.
I sometimes yes, sometimes not. It's a really a challenging thing, and having it put it that way, um, this is where we're challenging deeper theory, if not the Big Bang itself. And looking back at the history of science, it takes a long time to wrap your heads around these ideas. So, when Newton introduced the idea of the universal law of gravity, well, we just take that for granted and expect our first year students to pick it up right away. He wasn't sure where it came from himself. Um, and and a lot of people gave him a hard time to it because it seemed to them magical that there was action at a distance. How could that possibly happen? That the sun is reaching out and grabbing the earth or something like that. Um, and there are lots of aspects that we just have built into what we now call Newtonian dynamics that we take for granted, but took a long time to develop. For example, the Poisson equation is an essential tool that we use in the sort of analyses that we do of the dynamics because it relates the observed density distribution to the gravitational force. And
Okay.
there's just that's the Poisson equation. It's not named after Newton, right? That came decades later. It takes a long time to wrap your head around these things. And so I think we're still in that phase with these modified dynamics. It's telling us something, but we don't really know what that is yet.
Okay. Okay. So we don't know. We know that what we're looking at isn't support, does not, what am I trying to spit out? The observations don't match the Lambda CMD theory as well as they should. In fact, they don't
Yes.
match it very well at all. But what you did find supports MOND.
Right.
Um, so that means that we get, but how does that allow us to keep the Big Bang then? I mean,
Well,
can you
so
get it? Let's go back there. I'm still worried about the Big Bang.
that's healthy. We should worry about everything. It's just that some things are so well established, we kind of forget that we should
Okay.
worry about them. Um,
So
and and dark matter is such an example. I mean, when I first encountered this issue, I kept banging my head. How can this stupid theory, Mond, have any of its predictions come true when there's so much evidence for dark matter? And I really struggled with that question for a long time until I realized that there's evidence that something is wrong, but we don't actually know which it is.
oh,
And so you need additional observations like this to try to distinguish where the theories make a different prediction. And so the prediction in the case of Mond was that galaxies would form quickly. And that is just saying, okay, instead of dark matter, we've changed the force law of gravity. It's stronger now. It only works on the stuff you can see, but it works more strongly on that stuff.
in the past.
And well, in the past now,
Oh, okay. All right.
but the reason it did accelerate the rate of structure formation is because you have to ask which is stronger. We've invented the cold dark matter to speed up the formation process. We invented MON for the same kinds of reasons to give more force, but it's a different invention, so you have to see how they behave. And if you simply ask, okay, here's some region of the early universe that's expanding, but it's obeying this modified force law, how long does it take to collapse and form a galaxy-sized object? And the answer is about 500 million years. You can do
And
that, calculation. It's pretty straightforward. And what should take a couple billion years conventionally happens in that much faster time frame. And that's what Webb is seeing, that there are things that already seem
right.
to have formed that big, that fast, that early.
Okay. So this doesn't confirm MOND, but it adds support to
Yeah.
that particular model.
Yeah, it's the prior, right? I mean, as I said, you want to make your predictions before the observation. And in Lambda CDM, we had a clear prediction,
We
and it was
did.
that we should have all these little protogalactic fragments. In Bond, we had a prediction is that the galaxies would get big fast. That's what we're seeing.
Okay. So Are there other theories of cosmological formation besides those two that might fit the data, or
Well,
are these basically it for
yes
now?
and yes. So,
Yes and yes.
um, so
Okay,
yes, there
that's
there are
complicated.
lots and lots of ideas out there, and I don't want to dismiss them all. And it's tempting to dismiss Maud. I certainly tried hard to do that early on. Um, but
Hmm.
these are the two main games in town at this juncture. I'll put it this way: there's a contrast in scale. On the very large scales in the local universe, things have to look like Lambda CDM. It fits enough of the data that whatever your final answer is has to show that. Same thing for MON. There are lots of observations like this one, like the dynamics of individual galaxies, have to look like MON. And it's those two contrasts that really confuse me, because it depends on how you weigh the different lines of evidence. Here are these two incommensurate things that we've observed, and if you put all your weight on, oh, I only care about large scale structure, it's like, okay, well, Lambda CDM is the right answer. If you care about the details of dynamics and how galaxies actually work and how they could possibly form this early, oh, well, then MOND is a better theory. And we haven't figured out how to make those things mesh.
Okay, so we have another one of those things where we have two really good theories, but they don't mesh at the right spot, sort of like the gravitational theory and the quantum theory.
They
Okay.
hate each other, yeah.
Excuse me. Okay, folks, if you are just joining us, we are talking with Professor Stacy McGaugh, who is an astronomer, and we're talking about a paper that he's written about the formation of structure in the early galaxy. And what they found is it's bigger. The stuff we look at back there, the stuff we are seeing back there, is bigger than we expected based on the lambda cold dark matter theory of cosmic formation. And instead, it seems to support modified Newtonian dynamics, something called MOND. And if you're enjoying this talk, you will want to tune in tomorrow, because it's coming into Mars season. Mars is coming toward its closest approach, and we're going to have Debbie Bird will be here, and John Goss, who is our expert chart maker and an expert observer. They will be here tomorrow to talk about Mars and how to observe it. And then we've got a double whammy tomorrow. At that one, the first talk is going to be 12:15 Central Time. That is 18:15 Universal. And the second stream will be the sixth test flight. We're having a watch party, guys. Sixth test flight of Starship, the SpaceX Starship, will be tomorrow, and that's going to be, I want to say, 1:15 Central Time. And we're gonna watch them put that gigantic spaceship into orbit and hopefully catch it again. So tune in and join us for that. Anyway, back to Stacy and early galaxies, or early galaxies, very early galaxies. Um, so MOND, what's wrong with MOND? MOND doesn't describe everything. It has some weaknesses. Is that right?
For sure. For one thing, there are two big things I would highlight. One is
Okay.
theoretical and one is observational. And again, there's a dichotomy on which you care about. And as an observer, I'm more concerned about the observational one. But of course, there are lots of people who want to know the right theory. So they're concerned by the fact that MOND as a theory is an extension of Newtonian dynamics. So basically,
Okay.
Newton is a subset of MOND, but it is not compatible with Einstein's general relativity. And that's a big deal, right? General relativity is our foundational theory of gravity now, and has been tested in lots of precise ways. And so again, you have to recover all those successes if you're going to build some grander theory still that incorporates both general relativity and MOND.
Okay.
As you might imagine, that's not a trivial task. And so there have
Absolutely
been
not.
attempts. I'm not convinced that any of them are correct.
Okay.
The
So this is,
close maybe.
yeah, we wouldn't say that Newton was wrong. We'd say that Einstein was more correct and
Yeah,
developed upon
yeah,
that theory. And so that is that
exactly.
what we're seeing here?
Exactly. And so what we would like to see developed theoretically is a still more correct theory that can encompass both of these things. And
Something more robust that more exactly describes what we find when we look back into the earliest moments of our
oh
galaxy.
yes,
I
exactly.
just wanted to take a second. Uh, Elizabeth Lane, her eighth grade class in North Berwick, Maine, is watching us today. Hi, guys. Hi, welcome. And they just wanted to tell us that science rocks. Thanks, guys. We're glad you're here. Like and subscribe, everybody. Like and subscribe. And okay, so anyway, back. I just wanted to drop that in. Isn't that? It's. I'm great. I'm great. I'm glad. I think it's great that that we have kids interested in science,
That's awesome, and
isn't it?
welcome to all of them. I'm glad you're able to tune in. And the important thing about science is one to know things, but two to think for yourself. You can always register this, and I'm going to send a link to Matthew Hinson's question earlier, where there are images. There are lots of images online
Okay,
for web.
perfect. All right. So we had another question, which earlier came in from Matthew Henson. Are there any images that you can find us? Which one is the most important thing? And so Stacy has put a link into our chat, and I'm going to ask Will to transfer that over to the YouTube chat so that Matthew gets that. Okay. So what's next, Stacy? Where do we go from here with your exploration of the universe?
Well, let me. I don't know.
Oh, sorry.
So let me
Okay,
answer your other question. Finish answering it, because the other
please,
problem,
please.
big problem that Mond has, to my
Uh-oh.
mind, is in the data for clusters of galaxies. So Mond is extraordinarily good at explaining the dynamics of individual galaxies, and it does so over a remarkably large dynamic range, going from little bitty dwarf galaxies with a million
Big
stars
ellipticals.
up to things bigger than the Milky Way with hundreds and hundreds of billions of stars. And that is striking because, as you mentioned, one of my early discoveries was that these low surface brightness galaxies were dark matter dominated. And what attracted my attention to Mond was the fact that none of us predicted that, including myself, but Mond did. And basically, how dark matter dominated you appear to be as a galaxy depends on how spread out your stars are. The more spread out, the more dark matter domination. And so that was the only theory that got it right
Mm,
a priori. And it's still a theory that the only theory I know of that you can use to look at, okay, there's that galaxy in the sky. I can measure the distribution of its stars and gas. I can solve the Poisson equation for what Newton says it should be, and that doesn't work. That's why we
right.
need something extra like dark matter.
Mm,
But
not enough mass.
yeah, exactly. But the extra thing that Mon tells you is it's basically an extension of Newton. So it says, okay, you start with what Newton tells you, but here's an amplifier, and it lets you quantitatively predict how much amplification you get based on what you see.
Right.
That makes no sense in terms of dark matter, because especially in these low surface brightness galaxies, all the mass is in the dark matter. The stars don't matter, supposedly.
So if the
But
dark matter wasn't there, galaxies wouldn't hold together. Is that
exactly,
right?
they would just fly
Okay.
apart. And so
They
you
just
need something extra to hold them together, and that's what we
right.
thought was the dark matter. But
Uh-huh.
then the dark matter should be telling what the stars what to do, and that's not what we observe. It's the other way around. We can map out the stars are. We can use this strange formula that's in Mond, and that tells us what we are going to observe for the kinematics and where the dark matter needs to be. It's as if the tail wags the dog kind of
Mhm.
situation. So that's one reason why Mon seems to work better than dark matter.
Okay.
You do the same experiment in clusters of galaxies, which were now systems of hundreds, even thousands of individual galaxies all moving around. And it should succeed in the same way. And it almost does, but doesn't quite, right? It doesn't go far enough to explain that. And
So close,
so,
yet so far.
yeah, it is. It's just,
Oh, where do we go now?
and so
Good
it's
luck.
tempting to, and it is, where do you take it from here? And
Right.
it's tempting to just dismiss the theory because of this one failing. But if we did that, we would have thrown dark matter away a long time ago too. And so it feels like, the old parable of the blind man and the elephant, is that there's a problem and there are different aspects to the problem.
Right.
But they all feel like different things depending on how we approach the problem. And we're yet to really figure out what the whole is.
So they're not. So Lambda CMD isn't entirely wrong. Mond isn't entirely correct, and somewhere out there is a theory that we can use to unite these disparate observations into a singular explanation of how the whole general mishmash got this way. Which reminds me, folks, don't leave hydrogen just sitting around on its own. It'll turn on you. Look what happened. We just left all this hydrogen sitting around. Boom, universe. Careful. Anyway, Stacy, such a great explanation. That I would like to say I understand it better, but I don't think I can say that. You don't understand. I think we have a really good idea of what's out there and how our theories fail and succeed in describing what we've seen. And so that's probably where we're headed next, is more research, more observation, more description, more theorizing. What are you going to do?
Yeah, well, you always want to look more, right? And the JWST observations did come as a surprise to us, and that's surprising and that's uncomfortable, but it's also where we learn new things, and that's why we do science. So we want to keep exploring. We want to look deeper into the universe, both in time to early redshift, but also broader in space, to lower mass galaxies, these low surface brightness galaxies that I'm interested in. I got interested in because at the time they were barely known, and so it was new territory. And we learned a lot of new things from them, including things that falsified my own dark matter-based theories. And so, we have to always be exploring, and we also have to be open to the fact that maybe we're wrong. We've done that a lot, so it shouldn't come as too much of a surprise when it happens again. But it's hard to accept, especially with really well-determined theories,
I guess you have to remember that the folks who are out on the adventure, they don't have any idea how the adventure is going to end. It's only in retrospect. And so you're out there adventuring, you're out there discovering new things and surprising yourself, it sounds like, too. Speaking of discovering new things, I am going to plug I'm going to recommend that folks buy a copy of our really awesome 2025, there it is, 2025 lunar calendar. And this lays out the entire year in a single really nice print that you can frame and hang on the wall. And you can find that at earthsky.org. Okay, there's that. Awesome. Yeah, isn't that nice? This is really cool. I really like those.
I mean, as
really
an observer, I was always checking the phase of the moon. There are some kind of ground-based observations you really can only do in the new moon when it's completely dark. And
that calendar is perfect for it. It lays it out in nice diagonals. It really lets you see the rhythm of the year as it passes. Let you know where you are. Stacy, thanks again for joining us. Remember, folks, like the stream. If you got anything out of this, I think you did. I think everybody got a lot out of this. This was really good, Stacy.
It's a lot of fun to talk about these things, whatever you want to believe in. Yeah.
I can't wait to have you back. Go find out some new stuff for us to bring back and share, please. And speaking of sharing new things, we're going to be talking about Mars tomorrow in our early webcast, and that's at 1:15 Central Time, 18:15 Universal Time. And then later at 1:15, I believe it is. You know what? Like and subscribe and check the calendar. It's right here on our channel. You don't have to take my word for it. You can find it for yourself. Okay, Stacy. I thanks again so much for joining us. Remember, folks, is one Earth, one sky, Earth sky. We'll see you next time. Thank you so much for joining us. Bye, kids and Mrs. Lane's class.
Okay.
Okay. Are we clear, Nat?